Happy Wednesday, everybody. We are going to be jumping into a new topic today about differential equations. But before we do that, just a reminder, we have a quiz tomorrow, and the quiz is going to be over logarithmic, exponential functions, and integrals, as well as inverse trig functions, the kind of things that you saw on Monday when we had lecture. I'm going to go over two homework questions from inverse trig functions before I jump into the differential equations stuff that we're going to talk about today. The first, both of them come from section 5.9. The first problem is actually number 11, and I may not do the entire problem, but I may just kind of remind you. I think once you get the reminder of what to do here, you'll know how to proceed. So this first one is number 11. It's x cubed over x squared plus 1. Again, the degree at the top is bigger than the degree at the bottom, so we need to start with long division. So we're going to take our x cubed plus 0x squared plus 0x plus 0 and divide by x squared plus 0x plus 1 and see how we do here. So in order to get x cubed, I need to multiply x squared by x. So x times x squared is going to give me x cubed, no x squareds, and an x here. So when I subtract, I'm going to be left with a negative x. And notice the negative x is a smaller power than the x squared, so that means that we're done. So that integral up there becomes x minus the remainder here, so x over x squared plus 1. Okay, now that first thing I can definitely integrate. That becomes 1/2 x squared. This second thing, you might be tempted to do some sort of arctangent there, but again, remember that we got a du on the top, the derivative of the thing on the bottom. So here you want to let u equal x squared plus 1. Then the du is 2x dx. So that x dx on the top actually ends up being 1/2 du. So I'll let you finish that. But you're just basically going to get 1 over u. And then this part right here is going to be the 1/2 du. So that is now in a form that you should probably be pretty comfortable being able to do that. So the moral there is just to remember long division. When you have the power of x on the top is bigger than or equal to the power on the bottom. Okay, for number 28, this is similar to one that I showed you last time, but again, I just want to make sure you remember that so that you're not confused here. If the 3 plus 3 was not here, you would actually do a u substitution. If the 4x was not there, it was just a straight up arc sign. So what we're going to do is we're actually going to split this as 4x over the square root of 1 minus x squared plus the integral of 3 over the square root of 1 minus x squared. Okay. And for this first one, we do indeed do a u substitution. U equals 1 minus x squared. Du is negative 2x dx. So negative 1/2 du is x dx. So we end up with, we've got a negative 1/2 and a 4. And we've got a square root of u on the bottom, and the x dx becomes du. Okay, so this is now, that part, u to the minus 1/2, is something that we can definitely integrate there. We'll get there in just a second. This part right here is just straight arc sign. Okay, so that's just going to follow us as we do this. And so we've got a negative 2. U to the 1/2 divided by 1/2 is going to be multiplied by 2. And then you're just going to stick your u back in. So negative 4 square root of 1 minus x squared. Okay, so the key here is just to be sure to split that integral, because you're going to work with it in two different ways. The second one is just an arc sign, but the first one you actually have to do a u substitution. Okay? So we may have some extra time at the end. You guys may be able to answer some other questions or get some other questions answered. But I do want to go ahead and jump into the differential equations section. Now, I want to say something about the way that the book presents differential equations. It kind of throws you, if you were to read the section, it doesn't really explain what a differential equation is. It just kind of throws you into differential equations. And then section 5.7, it does start to get a little bit more into what is a differential equation, but not very much. And I think that's critical. We're not going to do a lot with differential equations in this class, but there are actually classes completely devoted to differential equations. So if you're an engineer or a mathematician, if you take some of these other classes, you will end up taking a class completely on differential equations. You may take multiple classes completely on differential equations. So this is actually a really important area of math. It applies in lots and lots of different areas. The idea is a differential equation, which we'll often abbreviate as DE or diff EQ. A differential equation is just an equation that involves, so it either involves the derivative of y or some higher derivative of y. Okay, so it can involve the first derivative, second derivative, third, fourth. It involves some derivative. Okay, and the idea is it's an equation that you want to solve. Okay, we want to solve for y. Okay. One thing that's critical here is that unlike other equations that you've solved before, so let me contrast this with something typical that you've solved before. So when you solve something before, like x squared minus 7x plus 6 equals 0, the solution to something like this is a number. Okay, so if we were to solve this, I would factor and I would get x minus 6, x minus 1. And then since the product is 0, one of them is 0. So x minus 6 equals 0, or x minus 1 equals 0. So x equals 6, or x equals 1. So there's two numbers that end up being my solutions. Okay, in a differential equation, and I'll give you, so an example of a differential equation would be y prime equals y. So a function whose derivative is itself. So the solution here is actually a function, or it's a collection of functions. One thing that you'll notice is that when you solve these numerical equations, you can have multiple solutions. The same thing can happen for differential equations. When we solve them, and we'll get into how to solve them, but when we solve them, we can have multiple solutions here, just like you have multiple solutions when you're solving a typical numerical equation. Another thing that's true is the way that we solve these differential equations depends on the kind of equation. So in the same way over here, if I give you a different type of equation, you're going to solve it in a different way. The way that we solve differential equations depends on the kind of differential equation that we're dealing with. And we'll look at I think for purposes of this class, we'll look at kind of two categories of two categories of differential equations that we can solve, and there's a specific technique that we use to solve them. Now, before we get into solving differential equations, one thing that's very easy is if I give you a differential equation and I say, is this function a solution? Remember, solutions are functions now. It's really easy to check and see if it works or not. Let me give you an example. Let's take the differential equation y prime equals negative y. Okay, the derivative, I want a function. This is asking me the question, what function has a derivative that is the negative of the original function? Okay. And then if I said, is y equals e to the x a solution? What I mean is, plug this in here and see what happens. So for example, if I take the derivative is just e to the x, and if I plug that in, is e to the x the same function as negative e to the x? No. So that means that this is not a solution. Okay? But if I were to say something like, is y equals e to the negative x a solution? Well, if we wanted to plug that in and see, we would say, let's take the derivative. To take the derivative, I've got a chain rule here. Derivative of the outer, plug in the inner, times the derivative of the inner. So the first derivative is negative e to the negative x. And now you should see that if I plug this in, negative e to the negative x actually equals the negative of the original function. So this is a solution. Okay. Let's try another one. Is y equals 4e to the negative x a solution? Is that a solution? Well, again, let's just plug it into the equation and see what happens. So I need the derivative. The derivative would be 4, same derivative as before, e to the negative x times negative 1. So plugging that back in here, I would see negative 4 e to the negative x. Is that the same thing as negative 4 e to the negative x? Yes. So you can see we end up with multiple solutions to this differential equation. In fact, these are not the only two solutions. There are many more solutions than just these two. But we're not getting right now into how to find the solutions. I just want you to understand what it means for something to be a solution. It's a function that satisfies that equation that you're given. Okay, let's take a look at another example here. Okay, I have an equation that says the second derivative of my function minus my original function equals 0. What that means is it equals the 0 function. Okay, let's try a couple sample possibilities here. Is y equals e to the x a solution? Okay, well, let's take two derivatives. So the first derivative is e to the x, and the second derivative is e to the x. And if I plug that in here, is e to the x minus e to the x the 0 function? Yes. Okay, so that is one solution. Let me ask now, is y equals sine x a solution? Well, in order for that to be a solution, let's take a derivative. So derivative of sine is cosine. And the second derivative, the derivative of cosine is negative sine. So if I plug that in, is negative sine minus sine the 0 function? No. Okay, so that is not a solution. So it's not too hard if I give you a if I give you a solution or something that might be a solution, a candidate solution for you to check. In the same way that if I gave you, kind of in the same way as if I gave you this equation, x squared minus 7x plus 6 equals 0, and I said, is 6 a solution? Well, you just plug in 6 and see if it works. Okay, I'm not asking you to find all the solutions, I'm just asking you if a particular thing is a solution. So that is not generally that hard. Now, if I ask you for, well, so one of the things that ends up happening, if you have so the differential equations are generally categorized into different groups. And one grouping that we often use is we talk about the order of a differential equation. Now, order means the highest derivative involved. Okay? So, for example, a first order differential equation means that the highest derivative that's there is just the first derivative. So, for example, y prime squared plus xy times y prime minus y cubed equals 0. That is a first order differential equation. The highest derivative that's involved there is just the first derivative. There's no second derivatives, no third derivatives, no higher derivatives than that. A second order differential equation means that the highest derivative that's present is the second derivative. So, for example, this over here would be a second order differential equation. Okay, and you can imagine you can have third order, fourth order, etc. Okay? So many times you'll hear the book and you'll hear me talk about the order of a differential equation. Now, when you have a first order differential equation, generally a pretty simple first order differential equation, the only ones that we're actually going to deal with we're not actually going to deal with anything second order or below. We're not going to deal with any of those here in this book. We're only going to deal with first order differential equations. Now, when you have a first order differential equation, many times what you can do is you can build something called the slope field. Okay, let me explain what a slope field is. So it's probably easiest for me to explain it by giving you an example here. So let's take the example y prime equals y. Okay? What I'm going to do is I'm going to draw some axes here, and I'm going to actually figure out a way to draw the solutions of this equation, even though I haven't figured out how to solve this equation yet. Now, what's interesting about this differential equation is that if you remember the derivative is another term for slope. Okay? Now, I want you to think of the slope as kind of like a GPS. The slope tells you what direction you need to go next, wherever you are. So let me give you an example here. Let's start with the point right here at the origin, 0, 0. Okay? If I'm at the point 0, 0, my x value is 0 and my y value is 0. And if I plug in x equals 0 and y equals 0 here, what you'll see is that the slope is 0 there. So if I have a solution that's going through the point 0, 0, the slope right there is actually 0. So what I'm going to do is I'm going to draw something with slope 0 right here, and I'm going to put a little arrow on the end of it that tells me everything's always going to be going to the right. This tells me that if I'm right here, my solution is going this way. Make sense? Okay, let's pick another point here. 2, 3. Okay, let's pick the point right here, 1, 0. Now 1, 0 has an x value of 1 and a y value of 0. So if I plug in y equals 0 here, then the slope right here is actually 0 as well. Well, that's interesting. What about the slope at 2, 0? What's that slope going to be? That slope is also going to be 0. Okay? Slope at 3, 0 is also going to be 0. Okay, so all of these slopes on the x-axis are going to be 0. Let's try another point here. Let's go 0, 1. Right here, at 0, 1, the slope would actually be 1. So I'm going to draw something in here with a slope of 1. Remember, a slope of 1 is at a 45-degree angle. Okay, if I'm at 1, 1, the y value is 1 there. The slope there is also 1. At 2, 1, the slope is 1. At 3, 1, the slope is 1. Okay, so I'm just going to draw everywhere where the y value is 1, the slope is 1. What about if the y value is 2? 0, 2 right here. Then the slope is actually 2, so it's even steeper. So I'm going to draw it steeper here. And then the slope here is even steeper. The slope is 3 here. Now, I'm only drawing arrows at certain points, but there are arrows literally all over this field. So for example, right here, at negative 1, 1/2, the slope, if the y value is 1/2, the slope is 1/2. So here, at these points, the slope is actually 1/2. So everywhere, there's an arrow. Okay, what about down here? If I'm at 0, -1, if the y value is -1, the slope is -1. So that means you've got arrows down here that actually go down like that. If the y value is -2, the slope is -2, so it's even steeper down. Okay. All right. So this is what's called a slope field. Now, what this actually helps us do is we can pick a particular starting point and imagine we were following the GPS of the differential equation and saying, right here, what direction do I need to go? And I start going that direction, and when I go out, I'm going to hit another arrow, which is going to tell me to go in another direction. And I go in that direction, and I keep going until I actually am tracing out a curve. And what happens in this case is that if I were to start at, say, 0, 1, I would start, as I keep going up, my slope keeps getting steeper and steeper and steeper. If I were to go backwards, my slope would be getting shallower and shallower and shallower. Okay, if I were to start instead at 0, 2, I would start out and I'd be going steeper and I'd just keep getting steeper. Here I would back out, getting shallower there. If I were to start at 0, 0, well, I would keep going on the x-axis, and each of these points would keep me going on the x-axis, so my solution there would look like this. If I were to start down here, I would start going steep negative, and I would keep getting steeper, so this would end up looking a little bit like this. So here you can see some sample solutions drawn here. So these are solutions to that differential equation that I can get by first drawing what's called a slope field, kind of like a GPS, that then tells me how I should move. Let's do a couple of other examples here. So let's take another example. Let's do y prime equals x minus y. Okay. All I want to do here is draw a slope field for this. Okay, so I'm going to draw some axes. We're not actually trying to solve this differential equation yet. Just want to draw what the solutions might look like. So when x, let's start with a point. We just start picking points and plugging them in and seeing what the slopes are there. So when x is 0 and y is 0, the slope is 0. So we're going to have a horizontal arrow right there. When x is 1 and y is 0, we're going to have a slope of 1. When x is 2 and y is 0, we're going to have a slope of 2, then a slope of 3, and it just keeps getting steeper. Back here, when x is negative 1 and y is 0, we have a slope of negative 1. And back here, we have a slope of negative 2, and it keeps getting steeper that way. Okay? Let's go up here now to 0, 1. At 0, 1, the slope is actually negative 1. Okay, and then at 1, 1, the slope is 0. And then at 2, 1, the slope is positive 1. At 3, 1, the slope is positive 2. Okay, and if we were to back out this way, it would just keep getting steeper there. Steeper negative. Okay, and at 0, 2, we've got a negative 2 slope, then a negative 1 slope, then a 0 slope, then a 1 slope, etc. Okay. Down here, if I were at 0, negative 1, the slope would actually be 1 here. Okay, and then right here, the slope would be 2. Right here, the slope would be 3. Here, the slope is 0. And here, the slope is negative 1. Okay, and then at 0, negative 2, my slope would be 2. Here the slope is 1. Here the slope is 0. Okay. All right, so let's try drawing in some solutions. Well, one thing that's interesting that I notice here is that if I were at this point, my slope is 1, and if I keep going on this line, you'll notice that the slope is always 1, which means that this line with a slope of 1, in other words, y equals x, is actually a solution to that differential equation. If you were to plug it in, you'll notice that if y equals x, this side's 0, if the derivative y equals x minus 1 is our, that's not y equals x, that's y equals x minus 1. That's where I was. So if I were to subtract that, this right side would be 1, and the derivative of x minus 1 actually is 1. Okay, if I were to start here and go, what you'll notice is that I don't keep going straight, because point over here, for instance, at x equals 1/2 and y equals 0 has a positive slope. So this solution actually ends up starting to go like this. And if I were to back it out, it ends up coming from something like this. Same thing if I were to start down here at 0, negative 2. Ends up coming from something like that. So these are all specific solutions that we just kind of get because we're graphing a slope field. Okay, let's do one more example, and then we'll get into actually how to solve some of these differential equations. So let's take the example y prime equals y times 3 minus y. Okay. So one thing that you'll notice here is that any place where my y coordinate is 0, the slope there is going to be 0. So every place on the x-axis, the slope is actually 0 here. Okay, let's look at what happens when y is 1. When I'm looking at x equals 0, y is 1, I get 1 times 2 is a slope of 2. Okay, so I have a slope of 2 everywhere here. Okay, at 2, I get 2 times, at y equals 2, I get 2 times 1 is again 2. But what you'll notice is that when my y value is 3, I get 3 times 0 gives me a slope of 0 again. Extend this just a little bit. When y is 4, you'll notice that I get 4 times negative 1 is going to give me a slope of negative 4, which is a really steep negative slope here. Okay, down here, when y is negative 1, I get negative 1 times 4. Again, this is a really steep negative slope here. Okay. So some example solutions here. When y is 0, the slope is actually always 0. So my GPS is telling me to always go to the right. So this y equals 0 is actually a solution. And if you try it, plugging it in here gives you 0. The derivative of that is also 0. Notice that if y equals 3, my slope is always 0 as well. So y equals 3 is actually a solution there as well. If you were to plug that in, this side is 0. The derivative of 3 is also 0. Now in between, if I were to start here, what ends up happening, and you might need to draw in a few extra arrows to sort of figure this out, but as you get close to 3, this number gets close to 3, but this thing gets really close to 0, and so the solution starts to level off in that direction and in this direction. Okay. Over here, if I were to start at 0, negative 4 and go in this direction, we actually end up getting steeper and steeper and steeper. So the solution down here might look something like this. Solution up here ends up coming in something like that. Okay, so those are, again, just some sample solutions to these differential equations. And if you're ever not sure, you pick another point in between and just kind of compute what the slope is there. You'll notice that anything that stays on this line is just kind of, it doesn't move. These two lines right here and right here are called, because you don't move off of them, they just kind of stay constant. These are called equilibrium. I'm out of the viewing range here. These two solutions right here are called equilibrium solutions. They don't move. Whereas over here, as you start going off, they end up they end up changing their y value. So those are not equilibrium solutions. There's a lot more that you can get into with those. I won't jump into too much here right now. But what you'll notice is that which solution I get depends on where I start. That starting point is sometimes given a name that's sometimes called an initial condition. An initial, think of it as kind of like an initial starting point. Okay, wherever I start, I get a solution based on that starting point. If I start here, I get this solution. If I start here, I get this solution. If I start here, I get that solution. So each solution has kind of its own starting point. Make sense? Okay. Now to kind of get to one of the main questions, which is how do we, if I want to solve a differential equation, how do I do it? Now, in general, solving equations, whether you're talking about numerical equations or differential equations, is super hard. So usually you can only solve equations that are of a special type, and then there's a certain technique that you use to solve them. So let me give you an example of a kind of equation that we're going to solve, and then I'll give this a name and we'll do a few other examples of this. So let's take as an example here, let's take the differential equation y prime equals 2x over y. Okay, I want to solve that differential equation. Well, it turns out that what I can do, I'm going to use the Leibniz notation, dy over dx. What I'm going to do is put all of the y values on the left side. So let's multiply this y up here to get y dy. And I'm going to put all the x values on the right side of the equation. So I'm going to stick the dx on this side. And I'm going to integrate. Okay, now this is a special differential equation that allows me to put the y's on one side and the x's on the other side. So let's integrate. Now if I were to integrate, what I would get on this side is 1/2 y squared plus c. And what I would get on this side, the antiderivative of 2x is x squared plus some other constant. Now, this is an arbitrary constant and this is an arbitrary constant. We don't need two arbitrary constants there. So if we drop one of them and just keep the other one, that's perfectly fine. Okay, because if I move this to the other side, I would get d minus c, and this is just some random constant. So I'm just gonna drop one of those two arbitrary constants there. Now I want to solve for y, so y squared is 2x squared plus 2 times this arbitrary constant, and so y is plus or minus the square root of 2x squared plus this arbitrary constant. And again, d can be anything, so 2d can be anything, so I'm just going to give that a different name. I'm going to call that c. Okay, and c is some arbitrary constant. So this is my solution to my differential equation. Okay. So what I see here is that if I have a differential equation, particularly a first order differential equation, where I can get all of the x's on one side and all of the y's on another side, then that differential equation has a special name. That is known as a first order. Okay, first order just means the highest derivative is just the first derivative. Separable differential equation. Okay, the idea of separable is that I can get my equation into the form where I have something involving y's times dy equals something involving x's times dx. So there's something here that's just a function of y and something over here that's just a function of x. So in other words, I can separate the x's and the y's from one another. And if I can do that, then I can integrate the left side and I can integrate the right side and then try to solve for y, just like I did over there, okay? That is called, if you can get your equation in this form, then it's called a separable, first order separable differential equation, and you just integrate both sides to get an answer, okay? Let's take a look at another example here. Let's suppose I have something like this. X squared plus 3y, let's do this. X squared plus 3e to the y times y prime equals 0. Okay. So I want to recognize that this is, in fact, a separable differential equation. So let's try inserting our Leibniz notation here, dy over dx. And I'm going to move the x squared over to the other side to make this negative x squared. And then let's move our dx over here. So 3e to the y dy equals negative x squared dx. And in fact, yes, this is separable. So I got some function of y times dy equals some function of x times dx. I got the y's on the left side and the x's on the right side. This is not always possible, and I'll show you an example in a minute where that's not possible. But because this is possible, let's go ahead and integrate both sides. So the integral of 3e to the y dy equals the integral of negative x squared dx. So I get the integral of e to the y is just e to the y. And I'm going to leave my arbitrary constant just on the right side. Over here, I get negative 1/3 x cubed plus some constant. Let's divide by 3. So I get negative 1/9 now, x cubed, plus some constant over 3. And this, since c is some arbitrary constant, it could be 1 or 3 or a million. C over 3 is just going to be some other arbitrary constant that I'm going to call d. You're going to see us do this a lot. When you take an arbitrary constant and multiply it by something, you just get another arbitrary constant, okay? So now to solve for y, I have e to the y. How do I solve for y here? Well, if you remember your solving techniques, what I need to do is take the natural log of both sides. The natural log and the e are going to get rid of one another, and so I'm going to end up with y equals the natural log of negative 1/9 x cubed plus that constant there. That is going to be my general solution to this differential equation. That is how I solve that equation there. Okay? All right. Let's try a couple of other examples. This is all we're going to do for the rest of our time here. So let's try another example here. So for example, let's do cosine of x times y prime equals sine of x. So we first need to figure out, is this separable so I can use my technique that I was using before? Well, let's try getting all the x's on one side. Let's make this into Leibniz notation, and let's get the cosine over on this side. So I get sine over cosine. And then let's stick the dx over there. Okay, and in fact, yes, we have function of y times dy equals function of x times dx. So it is separable. And if I integrate, you can integrate this one of two ways. The integral of dy is just y. Over here, this is tangent. Now you can remember that the integral is negative natural log of cosine. Or you can do a u substitution. U equals cosine. So then the du is going to be negative sine x dx. But this is one, the integral of tangent is actually one that I asked you to memorize. So I want you to get in the habit of recognizing that. We've got the integral of tangent there, and being able to trot that out there. Okay. Okay. All right, now for the most part, these generally aren't too bad. There is something that happens kind of weird with some coefficients sometimes. So let me give you an example here. Let's take y prime equals 2y. Okay. We'll look at this type of equation a lot more tomorrow. But for now, we're just going to solve this specific kind of equation. So I'm going to write this in Leibniz notation. dy over dx is 2y, and I'm going to put the y over on this side. So I'm going to get dy over y, and I'm going to put the dx over here. So this is in fact separable. I can take the y's, and I can put them on one side, and I can put the x's on the other side. And so now let's integrate both sides. So 1 over y, this is going to become natural log of absolute value of y. And over here, I'm going to get the integral of 2 is just 2x plus some constant. Now, I kind of did something wrong already. And kudos to you if you catch it. When you divide by something, you have to be super careful that that something is not 0. So what we have to do is we actually have to kind of take two cases here. If we're dividing by y, we kind of first have to take the case y equals 0. Now if y equals 0, the derivative is also 0, and if you were to plug those in, that actually works. So this y equals 0 is actually a solution. Do you see that? If y was the 0 function, constantly 0, then when you take the derivative is also 0, and that works in this equation. So that solution actually does work. When y is not 0, then you can do what I'm about to do here. You can divide by y. So you're going to see this happen in a couple of the other examples that we do here. What you have to take, if you want to divide by something, you have to be careful, and you have to take the case when y is not, when y is 0, and then when y is not 0. So here we're kind of considering when y is not 0. So we integrated, we got natural log of absolute value of y equals 2x plus c. Now I want to solve for y, so I'm going to take e to both sides, and e to the natural log just gets rid of the natural log. And over here I get e to the 2x plus c. Now I'm going to write that as e to the 2x times e to the c. Okay, because remember that's an exponent law that we have. Okay, now e to the c is an arbitrary constant. It can be positive, negative, or 0. E to an arbitrary constant, e to any number, e to something is always positive. So if I replace this with another number here, like d, then d has to be a positive number. Okay, so if I write this, for instance, as d e to the 2x, d can only be a positive number there. E to any number can only be positive. Now, let's drop the absolute value, and if I drop the absolute value, I get a plus or minus here. So now d, which was a positive number only, can now be positive or negative. If d were 0, we would actually get this solution. So what I'm going to do is I'm going to combine these solutions and this solution into one solution that's going to be y equals, I'm going to have to pick another number. Let's pick capital K, e to the 2x, where capital K could be positive, it could be negative, or it could be 0. And in the case when K is 0, I get the 0 function. So this is my general solution. Does that make sense? The weird part about this is having to look at these cases and kind of mess around with the with that arbitrary constant there. Let's do another example that kind of involves that. Okay. Let's look at, for example, x squared plus 1 times y prime equals 2xy. So there's my first order differential equation there. Okay, is it separable? Well, let's write the y prime in Leibniz notation. dy over dx. And let's try putting all the y's on this side. So if I put the y on this side, I still have my dy, but the y is going to be on the bottom. If I put all my x's over here, I still have my 2x. I'm going to stick the dx over here. And on the bottom, I've got x squared plus 1. So again, yes, this is separable. So now what I'm going to do is integrate both sides. And if I integrate the left side, I get, now again, I kind of was sloppy here. If we divide by y, we need to be careful of what happens when y is 0. So let's again take a case when y is 0. If y is 0, the derivative again is 0. And if I stick 0 in here and 0 in here, the entire thing is 0. So that is actually a solution. And so now I can consider the case when y is not 0, and that's what allows us to divide by y. Okay? If you ever forget, when you start dividing by something, that's the key to tell you, ooh, yeah, that's right. I need to go back and think about what happens if that's 0 and what happens if it's not 0. So when I integrate now, I get the natural log of absolute value of y. And to integrate here, I actually have to do a u substitution, right? So I'm going to let u equal the bottom, and the top is cooked up to be the du. So I've got the integral of 1 over u du. So that ends up being the natural log of the absolute value of u plus a constant. And let's substitute back in what u is. So u is x squared plus 1, and since x squared plus 1 is positive, I could actually drop the absolute value there. Okay, so now let's take e to both sides. I want to solve for y. If I take e to this side, that gets rid of the natural log, and I just get absolute value of y. Over here, I get e to the natural log of x squared plus 1 plus c. Let's clean that up a little bit. Let's write that as e to the natural log of x squared plus 1 times e to the c. Again, c can be any number. If we take e to any number, we get any positive number. So if I replace that with another number that I'll call d, d has to be a positive number. E and ln actually cancel each other, so what I get here is d. The e and the ln cancel each other, and I just get x squared plus 1. So absolute value of y equals some positive number times x squared plus 1, and if I drop the absolute value, y equals any positive or negative number times x squared plus 1. But y, if d were actually 0, that would also work. So we're going to let y equal some other arbitrary constant that I'll call k. times x squared plus 1. And that incorporates this solution and this solution here. So k can be any number. K is any number. Okay. Now I promised to give you at least just one example of something that's not separable. So let me just give you a very simple example. Let's do y prime equals x plus y. This is actually not a separable differential equation. So if you try separating it, if you put dy over dx equals x plus y, you might think, well, let's add the y over here. Or subtract it over. But when you multiply through by dx, that's great over here, but then you end up with a dx over here, and that's not good. There's no way to get rid of it. So this equation is actually not a separable equation. There is a way to solve it, but we can't solve it using these techniques here. So we, for now, we're not really gonna deal with something like that. Okay. I think the trickiest part to solving these separable differential equations is really just dealing with this this constant here, sort of turning it into e to the c, making that a different number, and when you drop the absolute value, getting a plus or minus. When you do this enough times, you'll get used to doing this because that actually comes up a lot. It just takes a little bit of comfort to get to that place. Okay? We will finish up tomorrow looking at a very special differential equation. But don't forget, tomorrow we're going to start with the quiz. Again, the quiz is over the logarithmic, exponential, and inverse trig integrals that we've already discussed. All right, have a great day, and I will see you tomorrow.